So again, we're told that 5% of the population of human has a disease. Ah, thank you. I am recording, but I'm not connected to the screen. Thank you, thank you. So 5% of this population of human has the disease. And we know that A1 is going to be the part of the population that has the disease. And then A2 is the part of the population without the disease. We are told that there is a test, and the test result B shows whether the disease is present. If B is true, it shows that the disease is present. If B is false, it shows that the disease is not present. We are told some information about this B, though, right? We're told that there's a situation where in 90% of the diagnosis, right, 90% of the test positive relates to actually having the disease. But then we're also told that there are some false positives. So when people test positive for something but don't have them, we call those false positives. So we're told this information, 5%. We can use the complement rule to figure out that 95% does not have the disease. And now we have to put all of this in our statistic language, right? So the probability of A1 of having the disease is 0.05, 5%. The probability of not having the disease, A2, event state A2, is 0.95. The probability of the test showing you have the disease when you actually have the disease is equal to 90%. And the probability of the test showing you have the disease but you don't have the disease is equal to 10%. So questions just on the setup and the information and kind of going from our yellow and green to our blue statistic speak. Okay, let's put all of this in a graph, or in a chart, sorry. So if we have a chart here where we have the events we have and let's go ahead and move this down. Okay. So we have the events here, and then we have the prior probability, also known as the P of AI. So we have disease A1, and we have no disease A2. And so again, we're told prior probability is 0.05 and 0.95. So that's just figuring out what our definition of prior probability is and putting that information from the prompt down there. Then we're asked about what the conditional probability is. So this is the probability of B given some AI. And so we know the probability of the test coming back positive given that you actually have the disease is 90%, and it's 10% of a false, oh sorry, not 10%. I am doing this whole thing incorrect. So I apologize. My brain wanted these two to equal 1, but they don't. And they don't have to. So this is actually a great teaching moment. This is 15% of a false positive. 15% of a false positive, not 10. So these two things, the conditional probabilities do not need to sum up to 1. My brain just attempted to do that, and it's incorrect. So the false positive is actually 15%, not 10%. And so this is where the material from the prompt drops off, right? We get 4 numbers from the prompt. We can put those 4 numbers into 4 places, but we have 2 more columns that we need to figure out in order to calculate our what are called posterior probabilities. So before we get to our posterior probability, we need to figure out our joint probability. And we know that our joint probability is the P of AI and that test being positive. And so we are going to multiply in order to get our joint probability here, right? Our probability of AI and B is equal to the probability of A, I, whichever one that is, times the probability of B given AI. And so for these, we're just going to take 0.05 and we're going to multiply that by 0.90. Which gives us 0.045. And then we're going to do the same for 0.95 and 0.15. And then our last part is we're going to figure out, okay, this is the joint probability of A and B happening. We're going to sum these two up, 0.045 plus 0.1425, which gives us 0.1875. And this is our probability of B. So just the probability of B not given anything. And so now we're going to take this probability of B and we're going to take these joint probabilities and we're going to look at the share of this probability that each one of these joint probabilities have. So when we are calculating what's called the posterior probability, which is also what we're calculating when we're using Bayes' theorem. So this is kind of the long way of going about it, and then we're going to use Bayes' theorem again, which is our shortcut. So the probability of AI given B is going to be equal to this number here divided by this number here. And so this is going to give us a 0.24 here. And then similarly, Gesundheit, we got 0.1425 on the numerator here and 0.1875 on the denominator here. So this gives us 0.76. And these two absolutely add up to 1. So posterior probabilities add up to 1. Conditional probabilities do not. So this is, like I said, the long way to getting to the answer that we were asked, right? If a randomly selected individual performs the test and the test indicates that the disease is present, what's the probability that the test is correct? So we know they have the disease. We're trying to figure out what's the probability that the test is correct when they have the disease. So that's one way to calculate the posterior probability. You calculate the joint probability, and then you look at the relative share of the joint probabilities for each event to get the posterior probability. The other way we can do it is we're going to use our shortcut, our Bayes theorem. Probability of A1 given B is equal to the probability of A1 times P times B given the probability of A1. Gesundheit. So on the numerator here, that's really just our joint probability, right? Just decomposed. And then on the denominator is going to be all of the individual joint probabilities that could occur, right? So we're going to have P of A1 times P of B given A1. So that same term from the numerator, we always pop it down in the denominator. And then we're going to look at the other joint probability, P of A2 times P of B given A2. So doing this, we find this guy goes here, this guy goes here, they also go here, that guy goes there, that guy goes there. So we end up with 0.05 times 0.90 on the numerator divided by 0.05 times 0.90 plus 0.95 times 0.15. So we get 0.045 on the numerator, right, which is our joint probability that we calculated. And then on the denominator, we get 0.1875, which is the probability of B. And so then we end up with 0.24. So we end up with the same answer. One way is through using a table. The other is through using Bayes' theorem. Hopefully that makes a little bit more sense compared to the very rushed 5-minute version that we did in the end of class on Friday. Questions on Bayes' theorem? It's mostly about understanding what the heck the prompt is telling you. Once you figure out this part, you're golden, right? Like once you can decipher what the prior probabilities are and what the conditional probabilities are, right? These are our prior probabilities, and these are our conditional. And you might only be given one of the prior probabilities, right? Because prior probabilities, these do all have to sum up to 1, right? But conditional probabilities, as we saw with my mistake, these do not have to sum up to 1. Question on our Bayes' theorem example here. Okay, awesome.